Dentist? That's no excuse. Okay. So you can do center of mass problems till the cows come home, right? All right. Very good. Easy. Say your origin where it is. Just don't get yourself screwed up like I got myself screwed up yesterday. Um, Now let's take a look here at this first one. Okay, when you see when you see questions like this first one, and by the way, this is the one that we're looking at, Jilly, while you're getting your teeth fixed. Was you getting braces?
No, just dentist.
Just dentist? All right. We'll publish this privately. We won't use your last name or anything. Talk about getting all your teeth pulled and getting dentures. I would hate to have dentures. How would you eat corn on the cob? Okay. So anyway, look at this. Now watch. If you've got a situation like this. Oh, here, let's take a look. Jilly. Now watch this. This is the same question, really. I have one billiard ball in this case. These all have the same mass. So when I let this go, look what's going to happen. This ball's going to stop, and that ball's going to go. Bump, bump, bump. So if this was an ideal system, if we just had two balls, which we could, I guess we could just have two balls. So if one hits the... See, it stops. Hold on. So, okay, so look at that. This is what's happening in problem one. I've got a 0.17 kilogram billiard ball traveling at 4 meters per second, head-on collision with a billiard ball of equal mass that is initially at rest. So take a look. This is my billiard ball number one. Bam, it stops, right? And it transfers the momentum to the other billiard ball. So the other billiard ball is going to have the same velocity and actually in the same direction. So it'll have 4 meters per second. Okay, question number two. Boy, I look pretty good with this new haircut. I'm digging it. So, not bad for a 60-year-old guy. A 25-gram marble sliding to the right at 20 centimeters per second overtakes and collides with a 10-gram marble moving in the same direction at 15 meters per second. Now, this is not an elastic collision type of a problem. Remember, for our elastic collision type of problems, we had V prime A is equal to MA minus MB over MA plus MB times V prime or times VA. Remember that? Okay, this is a different type of a situation. And then if you wanted VB, V prime B, that was going to be 2MA over MA plus MB V B. Okay, doesn't look like a B. So hold on to those equations.
Was it VA?
Was it VA?
Yeah, I think so.
And VA. So that's our V prime. Yeah, it would have to, because that's the object that's moving, because its initial speed velocity was 0. So anyway, a 25-gram marble sliding to the right. So we have 25 grams, and it is going at 20 centimeters per second. And there's this other 10-gram marble, 10 grams, and it's going to the right at 15 centimeters per second. Now look, conservation has to be conserved. I mean, momentum has to be conserved. So P1 plus P2 has to equal P1 prime plus P2 prime. Okay, very good. So let's go ahead and do that. Now, since everything's in centimeters per second and we're going to divide through, don't worry about changing to meters per second. As long as all the units are going to be the same, we don't have to convert. So we've got 25 M1V1. Let's rewrite this. M1V1 plus M2V2 is going to equal M1V1 prime plus M2V2 prime. Now, we're given everything in this problem. We're told 25 kg, is it kilograms or grams? So it's grams. You know, we'll leave it as grams. It doesn't matter. And we have 20 centimeters per second. And that's going to be added to 10 grams times 15 centimeters per second. And that has to equal M1, which is 25 grams. And we don't know, we're looking for V1 prime. That's what we're looking for. But we're told that the 10 gram ball, coin, or whatever it is, marble, goes now at 22 centimeters per second. 22 centimeters per second. So when you go ahead and calculate this, this is going to be 500. This is going to be 150. So the total thing here is 650. Kilogram meter per second. Kilogram meter per second. And over here, you're going to have 220. I put the wrong units on. This is going to be grams centimeter per second, and this is going to be grams centimeter per second. Okay, so then we just subtract over. So 650 minus 220 is going to be 430. So 430 divided by 25. Is 17.2 centimeters per second. And it's going to go to it's going to continue on that way. So this final velocity, V1 prime, is 17.2 centimeters per second to the right. Did you get that? Yeah. What's that?
We messed it up.
Messed it up?
I think it's because we had the equation like when one of them was stationary.
Oh no.
So then we had one.
Oh, okay.
Then we had
that would be
0.
That would be like question 3.
You're just completely missing that.
Well, there's no equation. It's just conservation of momentum. If I know that if my system initially, without any external forces, has a certain momentum, then after the collision, that momentum has to be conserved, assuming there's no friction or no external forces acting on it. Okay, makes sense? Okay, that is not a stationary collision. The next one is. So the next one, I've got chicken cooking downstairs for next period. We're making jambalaya. All right. So, a 5-gram coin sliding to the right. There's 5 grams sliding to the right at 25 centimeters per second. That's the velocity 1. And this is mass 1, or mass 1. Makes a head-on collision with a coin that is 15 grams and is stationary, initially at rest. Find the final velocity. Here's where you can use your equation. This one right here. So you've got your, remember this one is initially at rest, so you're gonna have V prime B. Okay, this is A and this is B in this case. V prime B is going to be equal to 2 times the mass of A, which is going to be 5 grams, times the initial velocity, 25 centimeters per second, divided by mass A plus mass B, which will be 20 grams. Okay, so we're going to have.
Can you just keep it in centimeters and grams?
Yeah, because then your grams will cancel, right? And then your speed will be in what's called. Yeah. So centimeters per second. So 2 times 5 is what? 10, right? So 10, and then I got 20 down here. So you're going to have 2.5 centimeters per second. 12.5. Yeah. 12.5. Easy peasy. Okay. So in summary, for collisions where one body is stationary and there are no external forces acting on it, we've got these equations, right? If we've got two things moving, whether they're head on or whether they're moving in the same direction and they collide, initial momentum has to equal final momentum. Okay. All right. Now, let's take a look at the hockey player sheet. That's the impulse one. Now, impulse. Okay, now here are the kind of questions we get asked for impulse. Let me just show you. So impulse is equal to force times delta t. Okay, force is also equal to mass times acceleration. So if for some reason I give you a mass and an acceleration and a time, you could calculate impulse, right? Because force is mass times acceleration. Now, another thing is that delta p, the change in momentum, is equal to impulse. So the change in momentum is equal to force times delta t. Okay. So let's say, for example, I have something with an initial kinetic energy and a final, or an initial momentum and a final momentum. So I have a ball. Let's say a ball is 5 kgs, and it's initially moving at 25 meters per second. Okay, and it collides with a tennis racket. I don't know why you'd be hitting a 5 kilogram ball with a tennis racket. It'd be a mighty big racket. But anyway, let's say it collides you hit it with a tennis racket, and the 5 kilogram ball is now moving at 35 meters per second. And let's say, for example, it was in contact with the racket for 0.12 seconds. What is the force that the racket exerted on the ball? You could do a problem like that, right? Because you know M1 V1, M1 V2, you can get the change in momentum, and you know the time, so you can calculate the force. Or if you know the force, you can calculate the time. Okay? So that's one kind to look out for. Let's take a look at this sheet and work through them. Oh my gosh. I hate Wednesdays. All right, so in this one, they're just saying that impulse J is equal to F delta T. So it says here, a football player kicks a ball with a force of 50 newtons. Find the impulse on the ball if his foot stays in contact with the football for 0.01 second. Oh, that's a tough one. J is equal to the force, 50 newtons times 0.01 seconds. So that's what, 0.5 Newton seconds? That's a tough one, boy. I bet you'd like to have 20 of those problems. I know Paige would. I'm not talking about Paige Keeney. This is a different Paige. Paige Keeney wants hard ones with integrals. Like this. Where we're doing line integrals, calculating magnetic fields and solenoids.
That's a Jilly question right there.
That's a Jilly question. You ever see that symbol before?
No.
You won't. No, that represents what's called a line integral. So if you have a solenoid, never mind.
No, we want to do it.
If you have a solenoid and you pass a current through it, you have to calculate the magnetic field in the solenoid using this special type of integral, and it's different than what you're learning now. Anyway, a hockey player applies an average force of 80 newtons to a 0.25 kilogram hockey puck. So 80 Newton force for a time of 0.2 seconds. Right? What is the impulse? Oh my gosh. Was it 16 Newton seconds? It's a tough one.
You don't have to worry about
No.
Screw mass.
Yeah, heck with mass. All right. Aunt Mary
Oh yeah.
No,
needs
man.
to hang her husband in her bedroom.
Oh,
Oh, wait, I read this wrong. Aunt Mary needs to hang a picture of her husband in her bedroom. She uses a hammer to drive the nail into his head, into the wall. Find the force exerted on the hammer. Ooh, the force exerted on the hammer. If so, force times delta T is equal to J. If the impulse is 25 Newton seconds and she wants the force and it's 0.5 seconds. So what's the force? 50 newtons, right? Easy. These impulse questions aren't hard. Okay. Oh, here's one here. Here's one with change of momentum. Impulse is change of momentum. So we've got plenty of time. Aunt Mary, come. A 0.5 kilogram basketball experiences a force of 10 newtons for a duration of uh, 0.1 second. What is the change in velocity of the ball? Well, mv1, the final minus initial mv2 minus mv1 is the change in momentum, and that is equal to force times delta t. Okay, so let's factor out an m, right? And this is delta v. That is the change in velocity. That is equal to force times delta t. So we are told the force is 10 newtons. 10 newtons for 0.1 second. Oh, I better put units on here. Newtons times 0.1 second divided by the mass, 0.5. So, so 10 times 0.1 is 1 divided by 0.5. So the change in velocity is 2 meters per second. Is that what you got? Yeah, easy peasy. All right. Oh, there's a back to this. Okay. A space shuttle burns fuel at the rate of 13,000 kilograms each second. Find the force exerted by the fuel on the shuttle if in 2 seconds the shuttle experiences a change in momentum of 325,000 kilogram meters per second. So 325,000 kilogram meter per second. Now that's the change in momentum, and we want to find the force. Force is just force times delta t is the change in momentum. Is delta p. So all we have to do is just take delta p and divide it by delta t. So we know the change in momentum and we know the time. So you just divide that number by 2. What'd you come up with?
162,000.
What?
162,500.
And the change in mode, that force would be newtons. Okay. Can't make these hard. Divided the change in momentum by the time. Okay. Exercise 3 really isn't, maybe we can take a look at it. A van of mass 1,200 kilograms was moving at a velocity of 8 meters per second when it was involved with a head-on collision with a lorry. You know what a lorry is? That's like British English for truck, a lorry. They have weird words in England for things. Like they don't say, do you want to have a cup of tea? They say, how about a cuppa? C-U-P-P-A. They're weird in Britain. That's why we had a revolution. Because we hated the way they spoke. So, this is I'm recording this, I guess. I shouldn't show this to my English fans. So a van of 1,200 kilograms was moving at a velocity of 8 meters per second when it was involved with a head-on collision with a lorry moving in the opposite direction. Assuming the van came to a stop after the collision, calculate the momentum of the van before the collision. Well, the momentum of the van before the collision is going to be just 1,200 kgs times 8 meters per second. So that's what, 9,600 kilogram meter per second. Okay, so that is my initial, what's the momentum of the van after the collision? Well, after the collision, what happens to the van? Comes to a stop, right? Yeah. So after the collision, it's zero. So my change in momentum is going to be negative 9,600 Newton seconds, right? That's my change in momentum. Find the change in momentum of the van. Well, it's going to have to be the same because the change in momentum is the change in momentum, but it would have an opposite sign. If the van took 0.3 seconds to stop, calculate the force that acted on the driver. Okay, so we know that delta P is equal to force times delta T. So delta T is 0.3. So that's going to be 3,200 newtons, 32,000 newtons. That's a lot of newtons. Right? Is that what you got? Not going to be a tough test, but you guys are going to have one of these type of fields where a ball is the AP, and you're going to have a ball here, and one ball's going to go there, one ball's going to go there, and I'm going to have to give you like an angle or a velocity, and you should be able to calculate that. Okay? So I think pretty straightforward. Like I said, we'll do part tomorrow, part Friday. I don't know what time my eye appointment is Friday. I don't know if I'll be here or not, but hopefully I won't come back with an eye patch on and a hook. All right, there you go, Jilly. Just for you. 23 minutes of my life gone. Have fun at the dentist.